tuned amplifiers. This is a very big topic, but for exam we'll simplify. The first thing, this is also called radio frequency voltage amplifier, narrow band amplifiers, like that. Some people call this as band pass amplifiers. That is also another name. Because tuning is required at radio frequency and the bandwidth is very less. Because at radio frequency the bandwidth is high, it's very tough. The best thing I will do is, I'll give you some questions and deal the whole concept. The first question is, why tuning at radio frequency? Why tuning at radio frequency? For example, I'll give you some options. This is audio frequency. This is also radio frequency. Audio frequency, this is C, D. Radio frequency. Audio means kilohertz, for example. Radio means megahertz. Suppose the bandwidth is 100, this is 10, this is 100, 10. Say for example, 100 means 100 kilohertz, 100 means 100 megahertz, 10 means 10 kilohertz, 10 means 10 megahertz. Here we have F1, F2. Here we have F0, F1, F2. What is the acceptable here? In audio frequency, if the bandwidth is 100 kilo, that is acceptable. But if the bandwidth is 100 mega, is very high, we can't afford to use such a bandwidth. And here I call it as wastage of bandwidth. Here I call it as, when the bandwidth is less, you can't accommodate. Bandwidth cannot accommodate signal. So this is wrong, this is wrong. Audio frequency bandwidth is more acceptable. Radio frequency bandwidth is less acceptable. This is not wastage, and at the same time it can accommodate signal. For example, you take a video signal bandwidth is 5 mega. 5 mega you cannot accommodate here, whereas 5 mega can accommodate here. This is called this is tune frequency. There is a tuning here, no tuning here. This is called untuned amplifier, wideband amplifier. This is called tuned amplifier, narrow band amplifier. When the bandwidth is less at tuning, though the center frequency tuned is for F0, bandwidth is F1 and F2. So what is the whole idea? Conclusion: The conclusion of the matter is 2 points. Audio frequency, more bandwidth, accommodates signal. Radio frequency, less bandwidth or narrow bandwidth, but still accommodates signal. So in other words, audio frequency, more bandwidth, that's called untuned. Radio frequency, narrow bandwidth is called tuned. So tuned amplifier, narrow band amplifier, radio frequency amplifier, all are same. Whereas at audio frequency, more bandwidth, untuned is also accepted. So what is not accepted? More bandwidth is wastage. This is wide bandwidth at RO, wide bandwidth at radio is not accepted. And narrow bandwidth audio also not accepted. Narrow bandwidth audio cannot accommodate signal. Wide band at radio, wastage of bandwidth. That's why the first question is, we definitely need tuning at radio frequency. That's the answer to my first question. Question 2. Which tuned circuit? That's the answer to be done. There are 2 types of tuned circuits. They are called series and shunt. Series circuit and shunt circuit. In fact, tuned circuit is also called resonant circuits. Resonance. Let me tell you 2-3 points about it. The frequency is 1 by 2 pi root LC. This frequency is also approximately 1 by 2 pi root LC. Z versus frequency is like this. Z versus frequency is like this. Like that. Z versus frequency is R. In other words, this is L by CR. Whatever the value may be, impedance is maximum, impedance is minimum. If you take current, where the impedance is minimum, automatically current is maximum. Current is minimum. Then comes the question, which one is good? More impedance is good or more current is good? Wherever more impedance is required, this is good. Wherever more current is required, this is good. But the point is, when we use this in amplifiers, we talk about gain. K0 is minus GM Z0. K0 is minus GM Z0. In any amplifier, GM into load, the load is at Z0. So when K0 is equal to minus GM into Z0 minus GM into Z0, here Z0 is great, therefore this is high. Here Z0 is lesser, that's why this gain is low. So low gain is bad, high gain is good. That's why parallel resonant is preferred to series resonance. Because when you talk about gain in general, minus GM ZL. In resonant circuits we say K0 minus Gm Z0. This is series. Series means minus Gm into R, which is very small. Whereas in parallel, minus Gm into Z0, where Z0 is L by CR. This is maximum. When the load is maximum, gain is maximum. Everybody wants more gain at resonance. For example, suppose this is a ETV. When you tune to that, you get the maximum output. That's good. Suppose if you take this ETV here, when you tune it, it will get a less sound. Less sound coming at tuning is very difficult. With a lot of difficulty, you have gone for tuning, but after tuning, this impedance is less, therefore gain is less, it is bad. That's why parallel resonance gives more resistance and more resistance gives more gain. Therefore, parallel resonance is preferred to series, because the shunt resonance circuit is also called parallel resonance. In fact, this parallel resonance is also called anti-resonance, because this is called axial resonance. What's the meaning of resonance, by the by? Resonance means current should be high. Because current is high, it is called resonant. Because current is low, it is called anti-resonance. Because in physics, we say anti-resonance means more sound. Here, electrical resonance, we say more current. Therefore, my answer to the second question is, which tuned circuit means parallel resonance is preferred to series resonance. Good? That's all. Question number 3. Which parallel resonant circuit because in the question number 2 we have finalized parallel is good. Question number 1 we said we need a resonant circuit, tuned circuit. Question number 2, which tuned circuit? Parallel. Then comes the question 3, parallel, which parallel? There are 2 types of parallel circuits. Okay, call this as circuit 1, this one, circuit 2, like this. So you are giving a signal here, RLC. Call this as circuit 2. Both are parallel resonance. Call this as RP, LP, CP, RS, LS, CS. S for series, and because these 2 are connected in series. Without too much of further discussion and waste of time, I want to say this is better because nobody will connect a resistor separately. Resistor is an unwanted quantity of inductor, unwanted quantity. Therefore, this being mentioned part of the inductor is better than this. But very luckily, both are identical. What is it? RP is equal to Q square into RS. LP is equal to LS. CP is equal to CS. So, whether they give this circuit or that circuit, you convert them and use as this circuit. When the conversion is possible, you can easily do that. So let us not debate on saying which circuit is better. Better we say any circuit is okay because there is an equivalence here. In fact, how these equations are being developed, with a simple idea called ZP is equal to ZS. For example, you call this as ZP, and what of the impedance comes here, you call it as ZS. If you equate them and equate the real values and imaginary values, you'll get this. Where the quality factor is, Q is nothing but quality factor. That's our question 3. Now I'm taking up a question number 4. Tuned amplifiers. Question number 4. That is, what is significance of quality factor? In fact, I said, what is the quality of quality factor? Quality factor is defined as Q, and Q means quality. Q factor is defined as energy storage by energy dissipated. Energy stored by energy dissipated per cycle. Because dissipation is power. Power is for periodic. Periodic is for cycle. That's why energy. This is half Li square by, say, Im. Im by root 2 whole square into RL by omega per cycle. If you write it half Li square by Im square by 2 RL by omega means omega will go up. Half of cancel, LL cancel. That is nothing but omega L by R. People call it as X by R. Reactance by resistance. That's the quality factor. If you consider capacitor, Q is 1 by omega C by R, 1 by omega CR. So therefore, quality factor is omega L by R, 1 by omega CR. That's the quality factor. What is the significance here? If quality factor is more, that means energy storage is more, energy dissipated is less. So dissipation should be lesser, because in an inductor R should be very, very small. If R is small, dissipation is small, that's the best coil. So the value of quality factor should be infinity ideally, but practically more than 10, less than 100. One of the greatest consideration and a constraint is 10 to 100. Greatest constraint is that. Question number 5. What is the significance of bandwidth? Significance of bandwidth. Look at anything like this. Frequency. Say this is voltage gain. Voltage gain maximum. Voltage gain by root 2. F1, F2, F0. If this voltage gain by root 2 is bandwidth, if it is power, this is power gain. Power gain by 2. That's why it is called half power points. half power points. That means the bandwidth is very significant. Anything less than half power, we are cancelling it. You can use it for other purpose. So, bandwidth is defined as duration of frequencies where power is half of maximum power. Say this is maximum, half of maximum. If it is less than half, you neglect this bandwidth and use it for some other purpose. That is why it is called conservation of bandwidth. Because we need to conserve the bandwidth and save the bandwidth, don't give bandwidth for less than half power. What is the link between this power and this voltage? When you take the square of voltage, power comes. That's why this is by root 2. Square of root 2 is half. So, bandwidth is the duration of frequencies in which power is greater than or equal to half of the maximum power. That's our question. Question number 6. What is the tuning frequency? Tuned frequency. F0. For example, you take a tuned frequency. For example, take this one, LR C. LRC. This being parallel, better take admittance. Admittance of L, admittance of C. So, admittance is 1 by R plus j omega L plus 1 by j omega C. Rationalize this, R square plus omega square L square j omega C. Omega C minus omega L by R square plus omega square L square. Any resonance frequency you want, put J term 0. Why? J term 0, there is no more storage, it is only dissipation. Put J term 0, you will get F0, that is omega naught C, omega naught L, R square omega naught square L square. Cancel it. R square omega naught square L square is equal to L by C. That's the value there. From there you can calculate F0. You will get 1 by 2 pi root L C approximately. For example, even now here you say if you neglect R, how much comes? Definitely that. Because as we have been telling, this is a coil, the internal resistance of this coil is 0. Coil is supposed to store the energy but not dissipate the energy. And what is the impedance here? If this is F0, what is Z0? Z0 is 1 by Y0. Y0 means at resonant frequency, this is R square omega naught square L square by R. What is R square omega naught square you got from here? Therefore, Z0 is equal to L by C by R, L by CR. That's what I told you. L by CR is the impedance that is for resonance. So, we got the resonant frequency, we got the resonant impedance. The impedance in parallel resonance circuit is L by CR. Classification of tuned amplifiers. There are two. Single tune, double tune. Single tuned is again two types. Single tune direct couple, single tune transformer coupled. Single tune direct couple again two types. Single tune direct couple, single tune direct couple. Direct couple, direct couple. Both are direct couple. This is F01, F02. F01, F02. If F01 is equal to F02, this is not equal. When they are equal, it is called cascaded single tune. That's why this is called single tune itself. But they are not equal, it is called stagger tune. So stagger tuned is nothing but a single tune where the frequencies are not equal. So single tune transformer coupled. What is that? You have a transistor, you have a transformer. But tuning wise only one, whereas here only one. Single tune transformer. Double tune क्या है? What is it? This is single tune. Another tune. Two single tunes are called double tune. Okay. So this is the first one. Stagger means same thing but not equal. So we have to study single tune direct couple, stagger tune, transformer and double tune. So I need to teach you 4 amplifier analysis. But then next question is question number 8. What are the requirements of tuned amplifier? For us to say any tuned amplifier is good, we need to tell some requirements. There are only 3. First one, variation of bandwidth should not affect selectivity. And vice versa. If you are varying the bandwidth, it should not affect the selectivity. If you are varying the selectivity, it should not affect the bandwidth. I mean, variation of gain should not affect selectivity. Gain is here. And bandwidth should be large enough. So variation of gain should not affect selectivity, variation of selectivity should not affect gain. For example, if you are going to another channel, for example, you are one TV, you are going to another TV, they should not affect the gain. Sound. Variation of channel should not affect the sound and sound should not affect the channel. Similarly, bandwidth should be large enough. When I said narrowband amplifiers, don't think it is so narrow. It should not be too narrow. If it is too narrow, it is a bad thing. Too narrow is a very bad thing. Why? If bandwidth is too narrow, signal is eliminated. Third and the last one is flat top skirt response. It should be like this. The top should be flat, like a skirt it must fall. Top should be flat, like a skirt it must fall. What is happening there? Suppose you have such a small thing, the bandwidth may be lesser. For example, this bandwidth is 10 kilo. This bandwidth is 1 kilo. Which is better? This is not better. Lesser bandwidth is good, but this is better because It is slowly changing, but this is suddenly changing. It doesn't have flat top. Top is not flat. Like a skirt, it is not falling. So flat top skirt response is not there. Flat top skirt response. In fact, all this is single tune. This is double tune. That's why double tune is better than single tune. Though the bandwidth of double tune is more, but it's better than single tune because it is slowly falling, it's bad. But suddenly falling is good. Because this is a pass band, eliminating it should be fast elimination. This is slow elimination. That's not good. So it's not a question of how much bandwidth you have, it is a question of how sharp they are falling down. So if three requirements are met, then we can call such a tune amplifier is better one. Question number 9. Analyze single tune direct couple amplifier. What is the feedback here or the circuit here? Like this, for example, call this as R02, RI2, R01. Because F01 is F02. All are identical. That is 1 by 2 pi root LC. Second one is K0 is minus GM omega L QE. It's not quality factor, it is effective quality factor, where effective quality factor is 1 plus omega naught Q naught by RI1, omega naught Q naught by R01, RI2. That's a quality factor. Thirdly, then the fourth point is K is K0 by 1 plus J 2 delta QE. Therefore, bandwidth is K0 by, if you calculate the bandwidth, K0 by root 2, you will get F0 by QE. Then what are the advantages there? Advantage is simple and cheap. But the drawbacks are many. Disadvantages are, first one, you see the response, how do you get? First one, variation of gain and selectivity. Variation of selectivity affects gain and vice versa. Secondly, bandwidth is less. Thirdly, no flat top. So all the three things are bad. That's what I mean. We are not happy about this. This is loading, therefore quality factor is decreased. Quality factor is less. Quality factor is less. That's called single tune direct couple. Question number 10. Analyze stagger tuned amplifier. Analyze stagger tuned. What is stagger tune? Is nothing but single tune direct couple. F01, F02. Just now we said K0 by 1 plus J 2 delta QA. Therefore, K by K0 is 1 plus J 2 delta QE. Suppose you say Jx, where x is 2 delta QE. what's the meaning of stagger actually? Please understand the stagger. If this is F01, this is F02, the overall will become like this. Overall. What happened there? Therefore, bandwidth is increased. Two single tune things like I taught in the previous one. That's why you do that. Then overall gain is K0 by K is equal to K by K0 into 1, K by K0 into 2. I mean first one, second one. K by K0 of first one, K by K0 of second one. So what will happen to this? 1 by 1 plus Jx minus 1, 1 by 1 plus J x plus 1. X minus 1, x plus 1. Why? Minus means this side, because this is original F0. F01 is lesser, F02 is higher. If you do all these calculations, you will get 1 by 2 into 1 plus 4 delta power 4 q power 4 QE power 4. Therefore, if you calculate bandwidth, root 2 times of F0 by QE. That's why bandwidth is increased. When bandwidth is increased, that's what we wanted. Then what are the advantages? Bandwidth is increased. Drawbacks? Gain and selectivity has a problem. No flat top skirt response. Out of 3, only 1 is satisfied. Bandwidth is more, gain and selectivity is get affected, and no flat top skirt response. That's why this is called stagger. What's the meaning of stagger? Added. Question number 11. Analyze single tune transformer coupled. Single tune transformer coupled. How is that? Say for example, you have taken this. This is a transformer. Output is V0. For that, the first one is K0 is minus Gm omega naught M into QE. What is M? Mutual inductance. L1, L2. Then quality factor is defined as 1 plus omega square M square by RC into R2. What is RCE? Output of BJT. R2 is, therefore, effective quality factor substituted. But if we compare with L and L, this is greater. So we can say the gain of transformer couple is greater than gain of single tune direct couple. Gain of single tune transformer couple is more than single tune direct couple. Why? Because M is greater than L. You see here, M is K into, so if this L1 is equal to L2, K is greater than 1, where K is coupling factor. That's a very good advantage. Third one is K is K0 by 1 plus J delta QE. Therefore, bandwidth is F0 by QE. Advantages: variation of gain does not affect bandwidth and vice versa. We are happy. Drawbacks: bandwidth is less, no flat top skirt response. Bandwidth is still lesser, flat top skirt response is not there, And if you see the response, you will appreciate my words. This is the response again. Is there any flat top? No. Is there sharp fall? No. Bandwidth is very less. Only one advantage, variation of gain does not affect bandwidth and vice versa. Question number 12. Analyze double tuned amplifier. Double tuned. Double tuned is like this. Here L1, R1, C1, L2, R2, C2. They both must have same quality factor. Therefore, L1 is L2, C1 is C2, R1 is R2. Literally identical tank circuits. We'll call it as Q. Second point is K0 minus Gm Q square by Q square R by 2. K is K0 by root of 4 delta power 4 Q power 4. Wherever there is power 4, bandwidth is root 2 into F0 by Q. That means bandwidth is into root 2 means increased. And if you see the shape of the curve, it is like this. Therefore, advantages. Bandwidth is more, variation of gain and selectivity not affected, flat top short response is there, flat top skirt response is there. That's why all the three requirements are met. These are being used nicely. Question number 13. Calculate bandwidth of cascaded tuned amplifiers. Cascaded. As we know, tuned amplifiers are so many types, but now it is two types. In some cases, bandwidth is F0 by Q. In some cases, root 2 times of F0 by Q. In some cases, K0 by root of 1 plus 2 delta square 4 delta square Q square. In some cases, 1 plus 4 delta power 4 Q power 4. Wherever square comes, this is. Wherever power 4 comes into root 2. In fact, this is single tune direct couple, single tune transformer couple, whereas this is stagger or double tune. Therefore, bandwidth of n stages is equal to bandwidth of first stage 2 power n minus 1. Bandwidth of this fourth root of 2 power n minus 1. So, this is the question they are asking. N stages, single stage bandwidth multiplied by this, single stage bandwidth 1. This is root 2, this is fourth root. That's how the bandwidth is get affected in different tuned amplifiers. Question number 14. Which response has better selectivity? Which response has better selectivity? For example, I'll give you 4 For example, this is 10 kilo, 20 kilo, bandwidth is 30 kilo, bandwidth is 40 kilo. Which one is better? Everybody says one thing, lesser the bandwidth, better the selectivity. That's what people say. But I said, provided shape of the response is same. If the shape of the response is not same, lesser the bandwidth is not that. Otherwise, flat top skirt response is better. Once again, lesser the bandwidth, better the selectivity, provided shape of the response is same. Otherwise, flat top skirt response is better. Now let me tell you one by one. Between A and B, what is better? A and C, what is better? B and D, what is better? C and D, what is better? A, B, C, D, what is better? I mean, between these two, lesser bandwidth is A, but is not correct. What is my statement? If the shape is same, lesser is better. Otherwise, flat top is better. So, B is better. Between A and C, same shape, lesser is better. Between B and D, same shape, lesser is better. Between C and D, different, this is better. Among all, B better. So if you say lesser the bandwidth, better the selectivity, that's not true. And another example is, this is all for single tune, this is for double tune. Double tune is better than single tune. Question number 15. What are the applications of tuned amplifiers? What are the applications? You have single tune, you have double tune. Less selectivity, better selectivity. So what is better? It can eliminate better. That's why this is RF section in super heterodyne receiver. Now what is used in radios and TVs today is super heterodyne receiver. This is RF section. This is IF section, intermediate frequency in super heterodyne receiver. This is called front end selectivity. This is called final selectivity. Front end means what? Selecting a channel. This is protecting the channel. There may be hundreds of channels in the TV. Out of that, one will be selected by this, but that being selected will be protected by noise and interference here. This needs to be more selective. That's why double tune is here and single tune is here. For you to understand super heterodyne receiver, I'll tell you two things. This is called RF section, mixer, IF, and so on. This is single tune, local oscillator, IF, double tune. So front end selection by single tune, final selection by double tune. Radio frequency, intermediate frequency, local oscillator, mixer. This is called super heterodyne receiver. So, that is the link, and that is an idea about this complete chapter, the very biggest chapter and toughest chapter, but in a very simple way to the examination point of view I have mentioned it, that is called, these are the 15 questions that normally come in the exam as far as tuned amplifier is concerned. Details you can take from any textbook, but this is the very important, difficult to understand